Hi, everybody. We had some technical issues with our recording of the beginning of last night's Geologists of Jackson Hole program, so I am going to re-record the introduction to the speaker. My name is Cynthia Blankenship. I'm the president of the Geologists of Jackson Hole, and I am co-chair of the Speakers Committee. And our speaker last night was Christina Riesselman, and Christina is a paleoceanographer and a 20-year veteran of Antarctic research. She has 10 Antarctic and Southern Ocean expeditions under her belt and has spent more than 2 years of her life at sea, using oceanographic research vessels as platforms to collect samples of the seafloor in the modern ocean. Originally from Bozeman, Montana, Christina holds a PhD from Stanford University and joined the faculty of the University of Otago in Dunedin, New Zealand in 2013, where she is an associate professor in the departments of geology and marine science. At Otago, Christina is proud to lead a dynamic research group that uses diatoms and biogeochemistry from a range of sedimentary and modern environments to examine the response of Antarctic, Southern Ocean, and mid-latitude systems to global change. She also promotes international cooperation through an ambassadorial appointment to the board of Fulbright, New Zealand, and a position on the governing council for the Australia-New Zealand International Ocean Discovery Program Consortium. In 2015, she was awarded the inaugural L'Oreal UNESCO New Zealand Fellowship for Women in Science. I hope you enjoy the talk. We sure did last night. Thanks, everybody.
Great. Okay, back to it. All right, so from there, I was off and running. I do have a Bachelor of Arts in English, but I've taken those storytelling skills that I developed as an undergraduate, added a major at the very end of my undergraduate experience. So I'm a double major in geology and English. For some time, thought that I might make myself into a science writer. And then when I went to work for, hide those floating controls, when I went to work for the, ocean leadership, or the Joint Oceanographic Institutions at the time, after I graduated with my undergraduate degree, I was working for the US organization that managed this major international ocean drilling program, right? So this is the JOIDES resolution. This ship spent 50 years sailing the global ocean as part of various programs and as the successor to a ship that was developed with ambitions to drill to the Mohole, which is something that some of you might be familiar with. So I worked for the nonprofit that managed this major international research partnership, and I discovered through doing that the thing I loved the most about this activity was the science. Writing about other people's science was fine, but actually engaging in the process of discovery the science offers was the thing that really inspired me. So from there, I went off to Stanford, did a PhD, was a postdoc with the US Geological Survey for a couple of years back in Reston, Virginia. And then my husband and I eventually made our way down to New Zealand, where we're both professors at the University of Otago. So in that role, I get to do some amazing things, and I get to do them with some amazing students. So up here in this top little picture here, this is me and a PhD student on a Korean icebreaker in 2015, collecting a whole bunch of cores from the Ross Sea. Over here, this is just about a year ago on the Italian icebreaker, Laura Bassi. This is one of my current PhD students, Megan Duffy, preparing some University of Otago coring equipment for deployment, again, in the Ross Sea. So it's a really privileged life. And I'm really grateful for the opportunity to come here and tell you some of the things, things that really feel meaningful to me that have been, that I've been part of discovering in the 20 years that I've been doing this work. So now, why am I here in Jackson to give you this talk? Well, as far as I can tell, it goes back to 2019 when the geologists of Jackson Hole made an excursion to New Zealand. And Mike Adler, this amazing man over here, was trying to find guides for your excursion. And he was over in in a drilling shack over on the West Coast. I don't know if Mike is on his way to Utah right now, and maybe in Utah, and maybe even in the Zoom audience. If he's not, I'm sure he'll listen to this. So he was in a drilling shack over in a location where one of my colleagues at the University of Otago had set up this major program to drill into the Alpine Fault. And Virginia had written her name up on the wall or up on some board. She's a very dynamic person. She'd written her name maybe all over the place. And Mike saw the woman's name and he cold called her to say, hey, I'm bringing a bunch of geologists from Jackson Hole to New Zealand. Can you be our tour guide? And Virginia wasn't able to, but she did connect Mike to a bunch of my colleagues at the University of Otago. And so when your group came down in 2019, the relationship between Otago and the geologists of Jackson Hole was born. Now, because of that relationship and because of connections, mostly between Mike and my head of department, Andrew Gorman at Otago Geology, when I had the privilege of bringing a whole bunch of New Zealand graduate students to the US with me this past June, and we set up an amazing road trip that took them from LA to Bozeman through some of the best geology in the American West, things that New Zealand students never have an opportunity to see in their home country. We connected with you folks. So we had just an absolutely incredible day in the park that John Heberger led for us, and Peter and the Mikes were along providing support. And it was one of the most, I think, most moving and dynamic experiences that our students had in their 2-week tour. So we are exceedingly grateful to your group for their generosity and for their time. And me being back here to talk to you is, I hope, a little morsel of payback. Payback's not the right word. Maybe this will be payback. We'll find out. But a small thing I can do in return to hopefully continue this relationship. So thank you so much for having me. Mike, if you're out there, thank you very much for taking me on an awesome snowshoe up to Taggart Lake yesterday. We were on snowshoes within 20 minutes of me leaving the airport. So that was a pretty exceptional way to arrive. Hi, Mike. I'm glad you're here. Right. So that's why I'm here in Jackson Hole. Why am I here as a scientist, right? Why am I here wanting to tell you some things about Antarctica? Well, it mostly starts with carbon dioxide, right? So we've got some carbon dioxide molecules. And for those of you who were at, dug around a little bit in your website or in the YouTube archives of your past seminars, if you were at I think the September talk, some of this will feel really familiar, right? So carbon dioxide generates an envelope around Earth's atmosphere. The more carbon dioxide we have in Earth's atmosphere, the more that, so when solar radiation comes through the atmosphere, hits the surface of the Earth, it generates infrared radiation. That infrared radiation tries to pass out through the atmosphere back out into space. The more greenhouse gases we have in the atmosphere, the less efficiently that infrared radiation can escape, right? And this is indisputable. CO2 in Earth's atmosphere has been rising since the Industrial Revolution. So CO2.Earth is a really nice CO2 tracker. They have daily updates. They have monthly average updates. Here, the most recent update that they've posted for monthly averages is for this past November of 2024. And CO2 in the atmosphere was 423 parts per million, right? Now, what does 423 mean in the bigger picture of CO2? Well, we're going to watch this little animation of how CO2 has climbed over the course of essentially the monitoring era. So what we're looking at here, I'll try to do this both with my mouse so the people at home can see, and then maybe with some fingers. So we've got a couple of long-term monitoring stations, Mauna Loa right here in the red dot, South Pole here in the blue dot, and those are the two stations that you see over here. Now, it's tough to see behind the play bar, but we're looking from 90 degrees south over here to 90 degrees north, and you can see time marching on over here to the right of the screen. And you can see that more and more little intermediary stations pop in. Those are our light and dark gray dots. And as time goes and time goes, this is from 1980, we can see this level creeping up and up and up and up. And you also see some seasonal shifts, right? So we've got this big seasonal bounce, mostly in the northern hemisphere. And in the southern hemisphere, the seasonal variability is a little bit less pronounced. So this is all about photosynthesis, essentially. You probably know that 90% of Earth's landmass is in the northern hemisphere, and a lot of it is boreal. So as plants grow in the spring, they suck a lot of CO2 out of the atmosphere, and overall CO2 falls. When they die or when they shed their leaves in the autumn, those leaves land on the ground, decay, and re-release carbon back into the atmosphere. So if you're looking at a snapshot of CO2 today, and you look in the northern hemisphere winter, that'll be about as high as it gets in the year. If you look in the northern hemisphere summer, or sort of latest summer, that'll be about as low as it gets. But see, I've just talked over something pretty important. Right, so we have these long-term monitoring stations. It turns out that we've been making continuous measurements of CO2, or scientists, and especially a group from the Scripps Institute of Oceanography, have been making continuous measurements of CO2 since the earliest 1950s, right? If you want to go back prior to the 1950s, we have to start pulling in Earth archives. So here we've got an array of high-resolution ice core data, and then we've got these very long, low-resolution ice core records. This will also be something that those of you here for the September talk were able to see. And what I'd like you to focus on is the idea that during past glacial periods, for most glacial periods, CO2 in the atmosphere hits about the same low level, right around 180 parts per million. For most of our last, I can pull this back and pause things. Let's pause that. For most of our last interglacial periods, right? So these would be our ice ages down here. For the last interglacial period analogous to what we're in right now, our natural level of CO2, and in fact, the level of CO2 in our present interglacial before the Industrial Revolution, is set right around 280 parts per million. There's a little bit of variability. We have some interglacials. This is marine isotope stage 9s. This is 3 interglacials ago. And the CO2 was just a little bit higher, sort of nudging up close to 300. And then some that are a little bit lower. And if you look in the geologic record, these with a little bit more CO2 were a little bit warmer. The planet was a little bit less icy. Then we have some of these sort of lukewarm interglacials that have slightly lower peak CO2. These were a little bit cooler. And in none of this ice core variability, right? So these are very cool records because people are taking microscopic bubbles of atmosphere. It's this fossil atmosphere that tells you exactly how much CO2 was in Earth's atmosphere when the snow lay down and was compacted. But we don't get anywhere close to where we started here with our pump handle, right? So we're really presently in an atmosphere that ice cores can't tell us anything about. So if we want to move, we'll move beyond the ice cores in a minute. At the same time that we see that CO2 feathering and rising and feathering and rising, we also see major changes in the Antarctic continent. So what we're looking at here is the rate of ice loss from satellite measurements over the Antarctic ice sheet. You can see that it's not uniform. This probably makes sense to all of you. We have some areas. Over here, we've got the West Antarctic Peninsula, where ice is being lost very, very rapidly, right? We're looking at the order of gigatons of ice per year in the mass loss. And then there are some places where increased precipitation is causing the ice to grow a little bit, right? So it's not a simple story, but we do have these regions where loss is rapid. And I'll talk a little bit more in just a little bit about what these regions have in common, mostly in West Antarctica, and then a couple of little spots around East Antarctica, where we're also rapidly losing ice. Right, so the relationship between warmer temperatures and ice loss in Antarctica won't be a surprise, right? I'm sure you see the relationship, like today, we see a relationship between a warmer temperature today in Jackson and slushier sidewalks outside. Now, I would say it's, what do I want to say about this? It's established reality that the warmer the Earth gets, the more ice we lose. And there are a whole host of other consequences, right, of warming the planet. And so in 2005, in 2015, the group of nations came together in Paris and hammered out for the first time a new path toward reducing CO2 for the whole planet. The concept behind the Paris Agreement was that no nation would tell any other nation what to do. Each country would be able to set their own national targets. Each country would be able to report the policy positions that they intended to take to reduce their national emissions, and that by all working together, all of these countries should be able to make a meaningful shift in this march toward a warmer and warmer Earth. Now, as part of this agreement, there was a pretty robust conversation about the consequences of warming for all kinds of nations and all kinds of consequences, right? So I'm here to talk about Antarctica, but there are food security consequences, there are weather system consequences. We've seen in California that wildfires will become more powerful and more unpredictable as we go forward. And based on a lot of climate modeling and an array of other approaches, the national leaders who attended the summit determined that 1.5 degrees of warming should be the global target for our warming cap, right? That if we can hold ourselves to 1.5 degrees of warming, that we ought to be able to arrest really the most dire consequences of climate change. But, should we slip beyond 1.5, that really 2 degrees was the absolute cap, the absolute top amount of warming that would not produce catastrophic consequences for the way humans occupy the planet, right? So the Climate Action Tracker, this is a group that monitors nations' progress and changes in policy and commitments, and then forecasts what that suite of global policies mean for the future of temperature. This is a little bit of a complicated figure, so I'll talk you through it. So based on, now I should also say, this is the picture from November. Climate Action Tracker has not released a new assessment since the change in administration. So the impact of shifting policy in the US isn't captured in any of the things I'll tell you today. But as of November, based on all the pledges and targets that have been submitted by all the nations that ascribe to the Paris Agreement, we were looking at a scenario that would put us right around 2.1 degrees C, with a pretty significant envelope of error, right? Maybe as low as 1.7, maybe as high as 2.7, but kind of the bare scratch of keeping us inside that beyond this we see catastrophe level. Based on policies in place, right? So not the commitments and not the aspirations, but the actual policies, we're looking at warming of sort of average warming of 2.7 degrees, again, with a pretty significant envelope of uncertainty, right? Between 2.2 and 3.4. And then we have this optimistic scenario, right? So if every single announced target and all the countries out there that say they're going to hit net zero by 2030 or 2050, if all of those policies were implemented and all of those aspirations were met, that would squeak us in right under that sort of there be dragons 2-degree warming level, right? So this is where we sit, and you'll notice that really none of these bar potentially the lower end of uncertainty for that optimistic scenario, bring us in at the goal. The other thing I should say is that in 2023, we had already warmed Earth by 1.3 degrees since the Industrial Revolution, right? So we don't have very much squish between where we sit now and that 1.5 degree. This is really what we should be doing, but if we miss it, we can do this other thing position. Right, and in order to achieve this, we actually need to start pulling CO2 out of the atmosphere, right? So that's a place at this point, for me as a geologist, thinking about how the planet changed in the past, I sometimes, I don't know, I feel like an oracle, like oracle yelling from the mountain into the void, right? The work I do is not going to be the work that makes change. The work that makes change will be the people developing new technologies. It'll be the folks figuring out how to adapt to the changes we're already seeing. It probably will be pretty significant carbon capture. It may be pretty radical geoengineering. And those are things that, that sort of sit uncomfortably if you have loved the Earth and climate that we have lived on for the last 50 or 60 or 70 years, right? So we are moving into a time of unpredictable change, no matter what we do. If we do nothing, we move into a time of unpredictable change. If we do some of the things required to hit this 1.5 degree target, we are probably also moving into a time of unpredictable change. So serious stuff going on. And in fact, we've got this sort of global average temperature anomaly relative to our pre-industrial baseline graph. Turns out that in 2024, we ticked over 1.5, right? So there is variability year to year. There's variability season to season. But we are also releasing CO2, not only at a high rate, but at an increasing rate. So this trend where we see gradual warming that's accelerating is likely, it's likely that the track we're on. Right, so that brings me back to this idea that we are really moving beyond what ice cores can tell us about how the Earth system operates in a high CO2 world. We've got our last 800,000 years. So this is 1, 2, 3, 4, 5, 6, maybe 7 glacial interglacial cycles. Again, we get back into the older part of the record and they're muted a little bit. And all of these glacial interglacial cycles were driven by Earth system interactions related to the shape of Earth's orbit around the sun, right? So sometimes, right, well, all the time, our orbit spins like a top a little bit. That happens on 21,000 and 19,000 year oscillations. Our orbit tick-tocks a little bit, right? So sometimes we're steeper, so you get more sun at the poles, and in the winter and less in the summer, or sorry, more in the, I guess more at 1 in the winter than in the summer. And then sometimes we are in an orbit that's more circular or more squishy, or more circular or more squishy, right? So that determines which season Earth is closest to the sun and which part of the planet receives more solar radiation. So this tick-tock is a 41,000 year cycle. This eccentricity, right, the roundness or squishiness or oblique or eccentricness is 100,000 year and 400,000 year cycle. Right now, we're in a climate on a planet where this eccentricity seems to be the dominant mode that triggers glacial interglacial cycles. We don't fully understand why eccentricity dominates. About 800,000 years ago, we shifted out of a mode where precession was the dominant, right? So precession ruled the roost for glaciations for millions of years, shifted into an eccentricity mode. But, none of these give us a planet, none of the ice cores give us a planet that even comes close to resembling the Earth that we currently live on. So where do we go to understand the Earth that we're currently living on? So now I'm going to take you on a little trip back to that kid holding the fish, standing next to Highlight Reservoir. Take you back to 1984 when I was a little kid holding a string of fish, and a radical debate about the stability of the Antarctic ice sheet was raging. And one of the major players in that radical debate was a person who I ended up learning from some years later at the University of Nebraska. So I guess the base of this debate was as follows. It's been 3 million years since atmospheric CO2 sat at the level that it sits today, right? So you have to go 3 million years into the geologic past to find an atmosphere with CO2 that's 400 parts per million or a little bit above. And this group of excellent scientists at Ohio State University at the Bird Polar Research Institute were tramping around in the Transantarctic Mountains, and they found glacial deposits back here along the back of the Transantarctics in places that look like this. And those glacial deposits contained marine fossils, right? So lots of things that some of you will be familiar with. Everybody's familiar with wood and leaves and fish and mollusks and insect fossils. Some of you might be familiar with microscopic marine organisms like foraminifera and diatoms and sponge spicules and ostracods. There were grains of pollen in this stuff, all sorts of things, right? And it turns out that those things, there we go, were full of 3 million year old diatoms, right? So this guy here, this is David Harwood. He's still at the University of Nebraska and remains a really important mentor to me at this point in my career. So David found this group of like very definitively Pliocene marine organisms in deposits 2,000 and 3,000 meters high in the Transantarctic Mountains, right? And so how do you take a whole diverse marine flora and fauna and transport it up those mountains? At the time, David and his advisor, Peter Webb, came up with this interpretation. So we have, as you'll recall from our ice melting insanely fast in Antarctica animation, where we have a lot of rapid melt over here in West Antarctica right now. This is a place where most of the Antarctic ice sheet is grounded below sea level, right? So the bed that ice sits on is below sea level. The same thing is true over here in the Wilkes Basin, over here in the Aurora Basin, those two warm spots that you saw in East Antarctica on that map. Right, so the interpretation or the explanation that Dave and Peter came up with for these really unexpected marine deposits up the flank of the Transantarctic Mountains was that there had been an open seaway, right? Like, and this is actually a pretty radical thing. I'm gonna do a quick, I'm gonna ask everybody. So actually first, has anybody here been to Antarctica? Excellent. Yeah, so it's not usually something I expect in a public lecture, but felt like in this audience, there might be a couple of people who've had the privilege of going. Right, so I'm gonna have you all close your eyes. Play this game with me real quick. Everybody, please close your eyes. And I'm gonna give you some choices for how thick ice is in the middle of Antarctica, right? So let's say, let's see, can I do this in, how are you guys, this is difficult. I'm gonna do it in meters. Hope you guys are comfortable with meters. All right, so eyes closed. How many of you imagine that, even you, please close your eyes. How many of you imagine that there are 30 meters of ice in the middle of Antarctica? Put your hand up. How many of you imagine that there are 300 meters of ice in the middle of Antarctica? How many of you imagine that there are 3,000 meters of ice in the middle of Antarctica? All right, hands down, 3,000 meters is the answer, right? More than a mile of ice sitting on top of this continent, right? So proposing that an open seaway had cut through that continent in a place where we now have 3,000 meters of ice, only 3 million years ago, when CO2 was just a little bit higher than 400 parts per million, was radical, right? That is a radical proposition. The base of the argument was that an open seaway allowed that marine life to flourish. Later, as CO2 dropped and glaciers flowed down off this highland, they would have eventually pushed up onto the mountains across the valley and smeared those marine deposits up into the mountains. Right. So a lot of people really thought this was lunacy. There were like super mean, angry fights at scientific meetings. Science fiction authors included this debate in science fiction. Like Kim Stanley Robinson wrote about this in one of his books, including these people by name. It was a big kerfuffle. And it was a kerfuffle that was not settled by the time I started my undergraduate degree at the University of Nebraska. So when I walked into one of David's classrooms in the latest 90s, and he, like in a casual conversation after class one day, revealed to me that we really still didn't know whether the East Antarctic ice sheet was stable enough to stick around through the last 400 part per million atmosphere. Like, I'll be honest, I was floored, right? You know, as a student, you think that the things you learn at a university, like it's all the stuff we know, it's the facts, it's the figures, it's the equations, you know. Turns out there is so much we don't know. And that's really where the science sits, right? And so that was a jaw dropper for me, and it really did change my trajectory and turn me into a scientist who was like pretty committed to figuring out what Antarctica did the last time CO2 was 400 parts per million. Right, so that brings me to the late Pliocene. I've got a couple of figures here from an older paper, and what you'll see, again, I'll try this with the mouse. So we've got a CO2 reconstruction. We're moving in because we have to move out of ice cores. We're moving into a space where almost everything I'll show you is proxy evidence, right? So it's finding material in marine sediments and other kinds of sediments that has a definable relationship to the thing I want to know about the past environment, being able to define why the stuff I'm looking at should give me a signal of the variable I'm interested in, and then stepping through time to reconstruct my variable of interest by using those proxies. So we've got a bunch of established proxies for CO2. These records are they're more highly resolved now than they were in 2013, but the story is the same. The last time we had CO2 above 400 parts per million during, and I should say this is only during interglacials, was about 3 million years ago, right? So at no point in the last 3 million years have any organisms on Earth occupied a planet with the same atmosphere that we have today until the year 2013, when we first rose above 400 parts per million. So from 3 million years ago until 2013, nothing that high. And this is also a time, so this is an oxygen isotope record. I'm not going to go into the details of oxygen isotopes today, but this is a record that tells us that the last time that the ocean was considerably warm was at the same time that CO2 was considerably higher. And these are a series of interglacials, right? Here's an interglacial, here's an interglacial, here's an interglacial. They're pretty easy to find in the geologic record because they have a definitive form, and there are a bunch of paleomagnetic reversals that sit right around that snapshot of geologic time. So that means that we can go all over the planet, find marine sediments, collect marine sediment cores that cover this little window of the geologic past, and essentially reconstruct almost anything you'd like to know about Earth 3 million years ago. So it's not a perfect analog for the present, but I'll tell you it's a pretty good one, right? So it had CO2 around 400 parts per million. Most of the continents and ocean basins were in about the same places as they are today, right? So we don't have to worry about plate tectonics, making currents and atmospheric circulation go in funny directions, had most of the same mountain ranges that we have, right? So all of the sort of physiography of the planet was already set to about where we are right now. A lot of modern plants and animals had evolved by 3.3 million years ago when this window opens. So we can use the things we understand about plant and animal habitat preferences today to make some inferences about the past. And this one is a little bit difficult, but it's true. The Northern Hemisphere was largely unglaciated 3 million years ago, right? So we didn't really start forming major continent scale ice sheets in the Northern Hemisphere until 2.8 million years. And like a sad thing to say is that that is the planet that we're moving toward right now, right? We have unprecedented rates of ice melt in the Arctic at the moment, including the Greenland ice cap. So we are really racing into a world where the Pliocene is a better and better analog for future change. So here is what we're contending with, right? We've got our present day with our rising CO2. We have a couple of those previous interglacials that you would have heard about in September, where sea level, even then, was 6 to 9 meters higher. And I need to pull out. I did myself some quick conversions today, so I could give this to you in feet as well, right? So 6 to 9 meters is, so 6 meters is just less than 20 feet. 9 meters is a bit less than 30 feet. They're closing the library. We get into the Pliocene and we're looking at a considerably higher sea level, which is going to be one of our lessons. So I won't give you the feet for that until we get there. Right. So the other thing I want to tell you about Antarctica is that it's not evenly glaciated, right? So we've got about 3 kilometers of ice over here in the thickest parts of the East Antarctic ice sheet. If all of that melts, we end up with 53 meters deeper sea level, right? So more than 150 feet. Over here in the West Antarctic, that part where the ice sheet is grounded below sea level, it's much thinner, right? So if we melt, and some of it sits below sea level already, if we melted all of the West Antarctic ice sheet, it would only be about 3.3 meters equivalent sea level. On Greenland, we have maybe 2.7. So losing all of the East Antarctic ice sheet is vanishingly unlikely. We've had big continent scale glaciers there for the last 34 million years, right, through much higher CO2 levels. So the interior of East Antarctica is stable for the moment, but some of those marginal marine basins have the potential to be vulnerable. So for those of you who haven't traveled to Antarctica before, I'm going to give you a gift. Oh, hold up. I need to plug in. Let's switch that for a second. Sorry, guys. I should have done this before I started talking. That end is for you. It's for me. Looks like we're good. Excellent. Thank you, Cynthia. Right. So I don't know if you guys on Zoom can see my fist. Everybody take your left hand, make a fist with your thumb sticking out. What we got there on Zoom. Okay, so this is, you're carrying an Antarctica around in the palm of your hand with you all the time. You can see over here, this is your West Antarctica. Here's the Antarctic Peninsula. This is where a lot of the excellent tourism operations go. I've never been here. I understand it's the most beautiful place on Earth. And you can see that your ice sheet through this region is quite a bit thinner. Your knuckles make the transantarctic mountains that go across. They form a backstop for this much thicker East Antarctic ice sheet. But you also have a few places where coastal embayments nibble into that. So those will be the areas where we might lose a little bit of ice, and we're currently losing a little bit of ice from East Antarctica. So there you have it, Antarctica in the palm of your hand. This one's west, this one's east, even though everything is north. Right. So I'm gonna hide those controls again. So I am an enthusiastic paleoceanographer. And what that means is that I spend a lot of time on drill ships and other kinds of ships out in the ocean, and sometimes on platforms that are sitting on floating ice, collecting samples of the seafloor. So here we've got the Joides resolution in a polar ocean with some sea ice. Drill string pops down, penetrates the seafloor, comes back up with a sediment core. This one is great. This is one that was actually collected from beneath the Ross Ice Shelf by the Andril program back in the sort of the late aughts. You can see one thing about this core, you can just use the nature of the sediments to infer change through time. So here we've got some green stuff. This is diatom ooze. Overlying it, you've got this rubbly stuff with a variety of grain sizes. In the top, we don't have any structure. This is probably familiar to many of you from the Jackson area. This is glacial till. If you find it in the ocean, we call it diamict. it's lithified. And then we have a little bit of stratified material in the middle that we think we see from the pullback of the ice sheet. So just the type of sediment can tell you things about the past, but what's in the sediment tells you even more, right? So I spend a lot of my time essentially as a paleontologist for microscopic organisms. These are diatoms. They're one of my favorite things. And that's a passion that I developed from my undergraduate education at the University of Nebraska. So in addition to these diatoms, I also use proxies like stable isotope geochemistry to understand changes in the surface ocean through time, and some radiogenic stuff. Today, we're going to stick with proxies that I think are pretty straightforward to describe. But if you're interested afterwards and you want to know more about some of the other properties of the ocean that we can reconstruct using other tools, I'd be happy to chat. Right, so that's our time machine. And now we're getting into the things we know, right? So these are our 5 lessons from the past. There are many others, but these are 5 that I think build a nice story. So the first thing we know is that Earth was definitely warmer, right? And in fact, it was about 2 degrees warmer than our pre-industrial baseline temperature. And that means that it's a really nice analog for the sort of Paris Agreement question. What happens if we miss 1.5 and make it all the way to 2? Now, when we talk about global warming and average warming, it's a little bit misleading, right? We see in this reconstruction, so these are a bunch of different sites where the sea surface temperature has been reconstructed using an array of tools, but all proxy reconstructions for that 3 million year window. You can see that warming, there's some warming at the poles. So the dots are colored here, where warm colors are places where the Pliocene was warmer than the present day ocean or the pre-industrial ocean. Cool colors are places where the Pliocene ocean was cooler than the pre-industrial ocean. And a lot of this warming is pretty modest, right? So here our sort of boundary between yellow and orangey yellow is 2 degrees, but we've got some places that were much, much warmer, right? I don't know if you can read the scale on the back, but some of these burgundy dots up there in the North Atlantic, those are places where the reconstructed sea surface temperature was 8 degrees Celsius warmer than pre-industrial. We also see warming in upwelling regions, right? So more warming in upwelling regions, more warming at the poles, a little bit of cooling at the equator, but no place was more than sort of 1 degree cooler than pre-industrial. So the proxy basis for this is some paleontology and transfer functions that take the microscopic organisms and convert them to ocean temperatures based on the present day preferences of those same organisms. And some of those are geochemical proxies. You put them all together, what we see, so here we've got a curve for our modern global temperature, and now we're looking at latitudes again. So minus 80 degrees, this is down here close to the South Pole, or as close as you can get to the South Pole with a sample from the ocean. The Arctic is an ocean, so we can get further north with these reconstructions. And what you'll see, so we've got our average reconstruction for 3 million years ago in the black, and then modern in the dots, and a modeled scenario in gray. And in all cases, you can see that the reconstructed line sits warmer than present day, and in the poles, it's considerably warmer, right? So that's something that we see right now. The poles are warming more quickly than the mid-latitudes and certainly than the equator. Right, so we also see warm anomalies in upwelling zones and modest warm anomalies in the Southern Ocean. So the locations of these temperature changes should have had a major impact on ocean circulation. Right now, the engine of thermohaline circulation that moves heat around the planet is mostly the formation of cold water when sea ice freezes up in the Arctic and down in the Southern Ocean. Sea ice freezes, the water is very cold, it gets dense, it's very salty, makes it more dense, and it sinks down into the deep sea, powering a conveyor belt around the planet. But if you don't have that cold water being formed in the North Atlantic, you would expect that the distribution of heat and the circulation patterns around the planet would be different. And in fact, that is what we see when we then go on and reconstruct the shape of circulation in the past. So this is my favorite way to look at Earth, partly from living in New Zealand, but mostly because it shows that we've really just got one giant ocean with a little bit of land sprinkled around it. And the Southern Ocean here is where our global ocean comes to mix, right? And you can see we have up in the Arctic, deep water forming and traveling into the ocean interior. And we're also forming deep water here in the Antarctic. And I want to tell you, water that sinks in the North Atlantic today goes all the way to 40 degrees south in the ocean interior. So how do we know that? It turns out that rocks hold the key. So this is a radiogenic isotope system. These are the isotopes of neodymium. And because they're radiogenic, one of the isotopes in the system is the product of radioactive decay from ancient rocks. And the time of decay for this system is on the billion, it's got a billion-year half-life, right? So essentially, every time a new rock forms, the neodymium clock is set, and the older it gets, the more of this daughter isotope it acquires. So when we look around the global ocean, we have some very, very old rocks, right? We have Canadian Shield, ancient Craton up here in the North Atlantic, where some of our deep water forms. And then down here around the Antarctic, we have younger rocks, right? So sort of intermediate age rocks. And that means that when those rocks erode, when glaciers push eroded material to the edge of the continent and dump it into the ocean, and seawater starts to dissolve those rocks, each of those water masses gains a really distinctive fingerprint. And those distinctive fingerprints travel all the way through the global ocean. So what we see here, over on this map, so I've told you that the current fingerprint of North Atlantic deep water is minus 13.5, just a number. The units don't matter a great deal. The fingerprint of Antarctic bottom water is minus 8.5. And we can see, so here this pink line is at that minus 13.5. So that's our fingerprint from water that comes from the North Atlantic going all the way into the ocean interior. You can see that up here in northern latitudes, so we've got 40 degrees north, this will be 60, this will be 80. That deep water mostly has that North Atlantic fingerprint. That fingerprint travels into the ocean as we go south and stays in this intermediate water mass, right? So this is our North Atlantic deep water. This is the engine of modern thermohighland circulation, all the way to 40 south. You can even see it coming up. So here's our 40 south. Our tick sits around 2,000 meters in the modern ocean. Now, this is an amazing material that when fish lose their teeth as they swim around the ocean, and those teeth are fossilized at the seafloor, they suck up neodymium like sponges. So we can go into these marine sediment cores, find these fossil fish teeth, analyze the neodymium, and know which water mass produced the fingerprint, right? So did that fish die? And did its tooth land on a seafloor that was bathed in North Atlantic deep water? Was it bathed in Antarctic bottom water? Was it bathed in something else? So by doing a series of these analyses, we're able to see that in the Pliocene, we have North Atlantic deep water essentially absent, right? So here's our Pliocene North Atlantic deep water end member. Here we have a series of cores from different water depths stepping down a ridge over here in the South Atlantic, and we see no hint of a North Atlantic fingerprint in any of those fish. We've also done reconstructions from other places along that travel path, and they do have North Atlantic deep water. But when we look into the deep sea, so this is now our North Atlantic. So we've got a shallow core here in light purple. So this one is from about 2,000 meters water depth. This intermediate purple is from 2,500 meters water depth. We have 3,700 meters water depth, essentially the entire water column, just no North Atlantic fingerprints whatsoever. And then over here on this side, we've got our modern water measurements, so measurements of water samples collected from the modern ocean, and then the structure of the water column from the Pliocene. So this reconstruction tells us that we had weaker circulation coming out of the North Atlantic. That makes sense. If you have a much warmer North Atlantic, that you wouldn't be producing deep water. but now we can definitively say that that was the consequence in the Pliocene, right? So we've moved our circulation. Okay, so we've moved our circulation. We're not getting our deep water from the North Atlantic coming into the Southern Hemisphere. What else do we know? Well, we know based on the assemblages of these diatoms and their established environmental preferences in the modern ocean that much warmer circumpolar deep water was impinging on the Antarctic continent. So the circumpolar deep waters came within 275 kilometers of the marine-based edge of the East Antarctic ice sheet and pushed this oceanographic front from its present position right out here all the way in, so snuggling up here close to the ice. So this is a primary reconstruction from this location. This is one of my IODP expeditions, and then additional supporting reconstructions from further around the Southern Ocean. And what we find is essentially this pair of little interglacials right there in our 3 million year window of interest, where we think this major front was unpinned from the bathymetric steering. So there are spreading ridges in the Southern Ocean that determine how these currents travel. We see this as evidence that that front was unpinned from its controlling ridge and was then able, so here's our controlling ridge here, was then able to spread out into this broad open plain around the Ross Sea, where we have a lot of vulnerable marine-based ice in the West Antarctic ice sheet, and then also closer to some of these basins where we currently see retreat from East Antarctica. Right, so this is an image showing modern, the sort of modern deep ocean, and this is the unnaturally northward position that those fronts occupy today. We think that moving into a Pliocene-like climate, we can just hop that current over, and then we have the danger of bringing considerably warmer water into contact with the ice sheet. So we're now looking at a cross-section of the ocean. It's a highly stylized view of what the Antarctic ice sheet looks like. Over here, we've got ice direction. Here we have the continental shelf and the shelf break going out into the ocean. You guys who think about glaciation being around the Tetons, you probably do think about this quite a bit. The weight of the ice in Antarctica actually pushes the center of the continent down. So we have this unusual reverse continental shelf where the shallowest part of the shelf is closest to the edge, and then it gets deeper as you go back to the ice. So that means that if warm water manages to pop up over that shallow shelf, it's essentially got the capacity to run away right there and eat away at the toe of that ice, allow rapid retreat. Right, so lesson 4, we know that marine-based ice sheets were at a tipping point, right? So this process that we predict from the position of our fronts, in fact, we see evidence that that was happening 3 million years ago. So looking at records from, this is the previous location, and then also a core collected from close to Ross Island, we see that just with that subtle tick-tock, right? So change in the angle of Earth's axis between 22.1 and 24.5 degrees over 40,000 year time scales. That was enough to cause full-scale advance, retreat, and collapse of the ice sheet every 41,000 years, right? So that is the core that I showed you in our initial image. We have these cycles going back to about 4.5 million years. And it turns out that that was happening under a not terribly warmer than present ocean, right? So we think the ocean was about 1 degree warmer than present when this was happening. And that degree was enough to stimulate this full-scale advance and retreat, much more dynamic than anything that we see in the present day. Right, so every subtle fluctuation in our solar budget triggered a major ice collapse. We also have evidence from, again, radiogenic materials, this time from looking at the composition of rocks that we think sit under the ice sheet from gravity surveys. And those reconstructions indicate that this part of one of these interiors, this is our vulnerable basin. We've flipped Antarctica upside down now, or right side up if you're from New Zealand. So this little basin here, we have evidence for rocks being eroded from deep, deep into the subglacial basin, and those erosional products coming out to these proximal cores at those same sort of key interglacial periods. And then all of this together won't surprise you to hear that sea level was actually quite a bit higher, right? So you retreat a lot of ice sheet because you've got a warm ocean in proximity to the submarine grounded areas. Our best reconstructions, and these are, they're tricky and there is some uncertainty here, but the best reconstructions say that the sea was about 22 meters plus or minus 5. So that's a big swing, but this is another number that I converted to feet. So that's 72 feet, just more than 72 feet higher than present day in the Pliocene. If you're looking at the details of this map produced by the Consortium for Ocean Leadership, you can see that we've lost a lot of low-lying Florida. The Caribbean islands are mostly away. San Francisco Bay is quite a bit bigger. We also have some interesting things going on up here in the Canadian Shield, right? So because this is before Northern Hemisphere glaciation, things like the Great Lakes, right, and Hudson Bay that were carved by glaciers are absent from this image. But, in order to get a picture like this, in order to get an ocean that's 22 meters higher than present day, means that we have to melt pretty much all of Greenland, pretty much all of West Antarctica. And then there's a little bit that comes from East Antarctica as well, right? So those submarine basins, those vulnerable submarine basins that were first postulated to be vulnerable back in 1984, now we know, right? So this thing that I was flabbergasted we didn't know in the 90s, now we know. The news isn't great, but at least we know, right? So some of the proxy basis for this comes from going over to the passive margin of North America and other places that are not very tectonically active, and just tracking paleo shorelines, right? So this is the Pliocene shoreline. If you go here, you'll find giant clams and all sorts of wonderful things. And it can tell us sort of how much higher sea level was 3 million years ago, right? So here it is, the Orangeburg Scarp. This would have been beachfront property 3 million years ago. Oh, and there are some of our giant clams. Right, so all of these lessons and more, there are many more, come together. So this is what the planet looks like if you warm it by 2 degrees, right? So Paris Agreement signatories say, well, if we can't hit 1.5, we really have to keep it under 2. Really keeping it under 2 is going to have some pretty significant consequences, right? There will be a lot of adaptation necessary to make us comfortable living in a plus 2 degree C world. And something else, so this is not something when I started doing this research, in my 20s, I started doing this research, I really, like academically, I knew this stuff was coming, but I honestly didn't expect to see like modern examples of the things that I've been reconstructing emerge so early in this process, right? So, we see the collapse of marine ice sheets happening already over in West Antarctica. We've got ocean circulation slowing down in the North Atlantic. We've got sea level rising faster than previously forecast, right? Sea level right now is rising 1/8 of an inch a year, which doesn't sound like a huge amount, right? But think about how many inches that is. Like, do the calculation for your life, and then do the calculation for your kids' lives or your grandkids' lives, right? Think about where the sea will be, and the rate is increasing, right? So the implication of missing that 1.5 degree target and sort of continuing on to 2, well, from an Antarctic perspective, it is the difference between an interglacial Antarctica that looks like this, with some artistic license, and interglacial Antarctica that looks a little bit more like Alaska, right? So we're looking at something a little bit more like Alaska and all of the attendant consequences that come along with that. For me, so I live in Dunedin, New Zealand. I've been there since 2013. The first year, we saw CO2 levels at 400 parts per million. And there are some really nice tools to understand sea level rise around New Zealand is invested in developing these tools, right? So we're tectonically active. We've got some subsidence problems. My home over here, if we go out to 2150, so that's a little bit more than 100 years, our sea level estimates, if we look at vertical land motion included, right, subsidence included, in this scenario, that's sort of our not quite Paris, but pretty close scenario, my home is looking at sea level that's maybe not quite a meter higher than today. And, for this room, I think it can be hard to imagine what 100 years means. These forecasts out to 100 years, they're certainly not on politically expedient timescales. But for me, I think about this in terms of my own home, right? So this is literally my home. That one right there is my home. And this is a photo taken in 1898, right? So this is 127 years ago, and there's my house, right? So if I look out another 127 years, will it still be there? I mean, I hope it is. My husband's also a geologist, and I should tell you, when we bought that house, looks pretty close to the sea, but we mapped the last interglacial sea level high, and we think we're going to be okay. Like, we drew a line through this neighborhood that we really wanted to live in and decided that we absolutely wouldn't purchase a house that wasn't above that position. But like 125 years sounds like a lot, but it's very much a human timescale, right? These are very human timescales that we're talking about. So, with that, I guess for you in Jackson, sea level's not the big worry, right? Your worries are more about what the atmosphere is going to do, right? And what your precipitation is going to do, what temperatures will do. And also, you'll have some concerns about like food system stability, right? So there are different worries if you have a beautiful home in the Tetons than there are for my beautiful home in Dunedin. But, I would say, actually gonna, let me see if I can think. Just going to pop through some of these because we don't need to belabor. I will say this. So a closing thought to plan is that the Pliocene is probably a fleeting analog for us, right? So here is this little window, the mid-Pliocene. Now we've turned those CO2 estimates into temperatures, changes in temperature. And we have some options, right? We have some pathways. So depending on how we elect to tackle this atmospheric challenge, we could go in many directions, but very few of them take us to a position that's lower than the mid-Pliocene, right? So maybe we're moving into a Miocene climate. Maybe we're moving into, so the CO2 level is similar, but the rate of change is literally unprecedented, right? So the last time there was a major release of greenhouse gases into the atmosphere, that was 56 million years ago, right? And maybe a contribution from methane hydrates, right? So frozen methane gas in the seabed, ocean got a little bit warmer, released some methane hydrates, bunch of permafrost, burned, pumped a lot of greenhouse gases into the atmosphere. Even that was an order of magnitude slower than what we see today. That was so much CO2 that 2 kilometers of ocean fully acidified, right? And the planet was 12 degrees Celsius warmer after that release than before. So might be a fleeting analog. It's a good, as people who think geologically, understanding the capacity for change, right? Like Earth's scale for change is, I think, is a superpower we have, right? So we can think beyond what humans see and into what the Earth has experienced. So the last thing I'll say, this is again from Climate Action Tracker, and it's a map, just tough to see on your screen, but on my screen, we've got gray outlining the countries that are invisible. I don't think I can do anything to the color here. But so what I'll tell you is that, so these are the sufficiency of commitments and policies to reaching that Paris Agreement aspiration. And and this again is from November, we're not really close with what we have right now. We're not really close. I mean, not only are we not close to hitting 1.5, we're at risk of skipping 2 entirely and moving on to 3 or 4. So, with that, I'm going to say thanks, and I'm happy to take questions. I know I looked at the schedule and it said 6 to 7:30. So hopefully you guys are okay with me yammering on for quite a long time, but thanks everyone for coming, and yeah, happy to take questions.
The Zoom question that says, what about continental subsidence versus uplifting faults?
Okay. Yes, so for people on Zoom, the question is, what about continental subsidence versus uplifting faults? So is that maybe if the person is still on Zoom, if they could clarify, is that a sea level question? So if that's I'm going to assume it's a sea level question until our Zoom friend says it's not. So there is, when you melt ice, there is a short-term, sort of a short-term rebound where places where the ice is melting, sea level actually appears to fall because the land bounces up so quickly. So there are some really nice tools out there where you can like play around at the IPCC. The most recent assessment report has a good one that will let you, so there are a couple of elements to that. So if you melt ice, let's say we melt a bunch of ice on Antarctica, the place that's going to see amplified sea level rise will be somewhere in the northern hemisphere. And in the southern hemisphere, there will initially be a period where sea level appears to be falling. And then as that isostatic rebound evens out, it'll end up being a global signal. The other crazy thing about sea level is that ice sheets actually have quite a lot of gravity. So when you build a giant ice sheet, so here, this is a picture of the East Antarctic ice sheet, right? And this is an area where it's grounded above sea level, right? So you see at the margin, some icebergs calving off the front, but just mostly sitting on bedrock. This ice sheet, because it has some gravity, sea level presently is a little bit higher in Antarctica than it is in some of the more distal parts of the planet. As this ice mass gets smaller, the gravity of the ice sheet reduces. So some of that water that's presently pulled toward the ice sheet will slosh back into the ocean and spread out. Hopefully that's a sea level thing. Awesome. And I should also say right now, the biggest contributor to sea level isn't melting ice. It's just that the ocean's getting warmer, right? So when the ocean warms, water molecules vibrate faster, they move faster, and they take up more space, right? Just like when you boil a pot of water, your water gets a little bit bigger. So most of the sea level rise we're seeing right now is from thermal expansion. But we're just now starting to see little bits of melt coming off the continent, and that'll we'll end up with a whole array of factors contributing to changes in sea level. Ultimately, more water in the bathtub is more water in the bathtub. Anybody else have any questions? Ooh, it's an excellent question. Okay, so for Zoom, the question is, what made it start to cool off again 3 million years ago? So there are hypotheses, right? I think we don't have a definitive indication. One of the hypotheses is that we finally hit an orbit that allowed the northern hemisphere to cool enough to reignite that production of deep water. If you're producing that deep water and you have a circulation that makes more upwelling in the Southern Ocean, you feed more phytoplankton, they pull more CO2 out of the atmosphere, and that'll trigger cooling, right? So there are a lot of Earth system feedbacks involved in all of these sort of all elements of climate. So I think if you look at the process, even just for the last glacial interglacial cycle, right? The process of building a big ice sheet and then so they build slowly, but then the retreat is pretty quick. And it seems to be a combination of, so changes in the orbit cause little shifts in the way the ocean circulates. Those little shifts in the way the ocean circulates, to build an ice sheet, you stop allowing deep water to ventilate back to the surface. So all the phytoplankton that settle through the ocean, as they decay, their CO2 stays dissolved in the deep ocean. And you sort of grow this big pool of CO2 interior to the sea. And then as your orbit shifts back, you warm just enough that that circulation can spin up again. And then the CO2 belches back out into the atmosphere, right? So there are a lot of these sort of multi-step interactions that seem to be the thing that drives the climate system. I mean, the natural climate system, the whole climate system, right? The climate system doesn't really care where the CO2 comes from. You know, the responses are going to be equivalent.
Do you have a view on the collapse of the North Atlantic circulation system?
Okay, so the question is, do I have a view on the collapse of the North Atlantic circulation system? I mean, my view is that it's coming for us, right? So I think so we're in, like, we have shifted into a climate state where we don't maintain sea ice through the summer any longer. We don't up in the Atlantic, or sorry, in the Arctic. So the Arctic is really different from Antarctica in that the pole is all ocean. So you can't grow big ice on the poles, but you can really change the global climate by the amount of sea ice that you're forming and the way that, you know, so it's a density stratification thing. Water gets cold, the sea freezes at minus 1.8 degrees C, right? So freshwater freezes at 0, the sea freezes at minus 1.8. So the water produced when you have sea ice freezing actually gets down to minus 1.8. And then when that sea ice freezes, it freezes essentially as a freshwater ice lattice. It has little bubbles of briny stuff captured, but most of the brine gets ejected from the sea ice lattice. So you end up with super salty, super cold water sinks into the deep ocean. The less we're growing sea ice, the less we'll see that sort of density stratification set up. And you know, as I said, and as you might have seen in the news over the last couple of years, there are already indications that circulation out of the North Atlantic is becoming more sluggish. So that's a big problem for, I mean, not like for tomorrow, but for decades down the track. It's a big problem for Europe because they actually get bathed in weirdly warm climates because the Gulf Stream propelled by, sorry, I should be doing this in your direction, right? The Gulf Stream propelled by that global thermohaline circulation carries warm water up to latitudes that are pretty cold over here in the northern or in North America. So that's, I mean, that's my opinion about the North Atlantic. Yeah. Any other questions? It's like I said at the start, I say these things and I sort of feel like, you know, it's like the hermit in the woods screaming into the void. And I don't, you know, I get to the end of one of these and it's always kind of a bummer, right? So what do we do? And you know, what I tell my students is that like what a pass the buck, right? But the kinds of technologies and the kinds of innovations that people are thinking about today are, you know, like I would not, if a kid came to me today and they were like, I love what you do, should I study this? I would say, well, you know, if you love it, you should do the thing you love. But if you want to do this to try to solve the climate conundrum, go be an engineer, right? like go develop technologies and innovate ways to get some of the CO2 out of the atmosphere. And the last thing I'll say, so that I think a lot because I don't know, right? Like I think a lot about stewardship, and probably you guys do too, right? Like you grow up in a place like this, or you have the privilege of calling a place like this your home. You really feel a responsibility to be a good steward. So my experience of stewardship started as a kid in Montana, but it's grown to encapsulate all of these places. And so, you know, prospects like geoengineering make me feel really nervous, right? Like how can you both be a good steward of a natural environment and also commit to making major changes to it. But I've also been thinking, right, like before the Industrial Revolution, industry, like machines were lubricated with whale oil. Street lamps were powered by whale oil. There's like the whaling industrial complex. And so was the Industrial Revolution like an unmitigated bad thing here now that we are 150 years down the track and we've seen what the consequences are? I don't think it was, right? Like the Industrial Revolution gave us a great deal. And now it's our responsibility to consider how to, now that we know the harms, to consider how we manage those harms. So, you know, maybe geoengineering is a thing like that. We can't predict, you know, if we seed the ocean, if we go out with half a battleship and grind it up and feed all those plankton more iron, we can't predict what unpalatable consequences might arise. But if it resolves a problem that we have in the immediate term, I don't know, like progress is always scary.
It looks like there's a lot of interrelated causes and effects. For example, we've got ocean temperature versus CO2 in the atmosphere. Oceans go up, temperature release CO2. Oceans cool, absorb CO2. That's not a negative feedback cycle. That's a positive.
No, those are positive feedbacks.
Positive feedback should be taken into.
Oh, almost certainly. Yeah, there almost certainly are, and I don't have the expertise to. I mean, like so. I spend day and night thinking about the ocean, and I'll be honest, it's not actually like I'm a mountain kid. I don't think about the ocean all day and all night because the ocean is the thing that like fuels my heart. I do it because it's where the sediment piles up in a way that's interesting. If I could find these records like up in the mountains and go collect them there instead, I would probably do it. But because I use ocean sediments, I think about all of these questions from an ocean lens. I'm certain there are like landscape contributors, right? And things in the landscape that'll be sort of playing into those feedback loops. Anybody else?
Wow. That's
Thank you guys. Thank you, everyone. And thank you to you folks on Zoom as well.